Today we're going to look at the de Broglie hypothesis, and we're going to state and apply the relevant equation. The first thing you're going to do is have a look at this very, very interesting experiment you may have seen before, which gets to the real heart of quantum physics. The quandary of whether something is a particle or a wave. So click on this link and have a look at the craziness that is quantum physics. So the key issue at that last video was this quandary that particles can behave like waves or they can behave like particles. And the fundamental aspect is the actual test itself. At that point when the phenomena is observed, a decision's made. So what we've got there is a duality which depends on some kind of external interaction. We're going to take that one step at a time. And that explanation starts with Louis de Broglie. He was a French physicist who considered this wave-particle duality, which was going on and accepted. It looked at the idea of light as particles and considered the opposite. He considered that if waves could be particles, perhaps particles could then be waves. And he considered this theoretically. At the time, he was just a graduate. So he was an undergraduate and he was considering some very high-level arguments already influenced by Einstein. However, it was his doctoral thesis in 1924. He was very, very young, where he stated that any particle having a momentum p, or mass times velocity, remember, will have a wave associated with it having a wavelength of lambda. And it would be equivalent to Planck's constant divided by the momentum. So that's pretty much the de Broglie hypothesis. Wavelength equals Planck's constant divided by the mass times velocity of the particle. And this is the applied equation. Now that was a theoretical proposition. The entire physics community was pretty much working together in trying to push these kinds of ideas forward. And in the US, some experimental evidence was on its way. Davison and Germer had an experiment that indeed confirmed the electron was a wave. Now for this, we need to consider diffraction and interference first. Diffraction and interference are fundamental properties of waves. Diffraction is the behavior of a wave as it goes through a slit. It's curved behavior as it moves through a slit that's smaller than its wavelength. Interference is what happens when two waves interfere or affect each other's flow and creates these maxima and minima. When you get waves interacting in such a way that a maximum amplitude hits a maximum amplitude, you would get a maximum amplitude. When you get a maximum and a minimum amplitude, they cancel out, and you get these areas where there is no wave at all. This cancellation, which is evident in every wave from light, sound, water, etc., is a fundamental property of a wave. What Davison and Germer were trying to do is illustrate that this phenomena, which is associated with waves, can be found in particles. And they looked at the electron. Now I need you to watch this video. This video illustrates the experiment that they did. Their gaps are the boundaries between the atoms in a crystalline substance. I think we've mentioned this before, but any substance that is arranged in crystals would have gaps between the individual crystals themselves. These gaps provoke an opportunity for diffraction and interference, but they were using an electron beam. Now I'll run through the cathode ray for you again. What a cathode ray does is it enables electrons to get to a stage of energy or a high energy state so that they can be removed. Now that's done by having a metal, a very, very hot metal wire or a filament, which is heated up in a circuit. So this is the first circuit. These electrons would be very, very excited because they're very hot. And then what you do is you apply a positive terminal here, which will accelerate them. So these electrons will be attracted, and you get a thin, thin beam of electrons here. The reason why it's a thin beam and not just a messy mass of electrons is because you have a tiny gap here. You'll see that in a minute. So Davison and Kerma used this thin beam of electrons. They fired it at a crystal line structure here, and they measured the resulting path of the electrons on the other side. So watch this video first and we'll discuss the results. So you'll understand now that their movable detector, as they moved it along, saw areas of maximum intensity and minimum intensity. They saw a diffraction and interference pattern for their electron beam. Okay, so depending on that alignment, they would see areas of maximum and minimum. These diagrams aren't on the syllabus, so don't worry about them too much, but they illustrate the actual results that they got. So what's really important about this? Well, it proves de Broglie's equation. It proves that particles do have an associated wavelength, and their results were calculated using de Broglie's equation. They matched up. Theirs was not the only experiment that illustrates this kind of wave structure to particle motion. You can also look at a simple cathode ray illustration. So have a look at this last experiment, as it will illustrate the second way that you can prove that an electron behaves like a wave. And if an electron can behave like a wave, pretty much every other particle can too. Now this gives us a crazy conclusion, which is, well, if the atom is, at the end of the day, mostly empty space, apart from a little chunk of matter in the middle, and that little chunk of matter is actually a wave, there pretty much isn't such a thing as solid matter anymore. But we'll leave that for another day.